Alrighty, guys, let's get into it. Let's continue Unit 5. So we're gonna get started right now again with a new equation. So we talked about how if we have a mixture of gases, right, that the total pressure is the sum of all of the pressures of all the gases that make it up, right? Now, since the ratio determines the pressure, we can also use that to find the mole. So we can also find the mole fraction of a specific gas in a mixture using this formula right here. It's the fraction formula, percent formula, stuff that we've been doing, but this time just with gases. Why isn't it staying on? All right, so let me show you guys how to use this equation. It's very simple. When you have a mixture of gases, so we got a mixture right here. It says that we have a mixture that's made of 1.5% CO2, 18% oxygen, and 80% argon. Okay, and that's the percentage by mole, and we have the total pressure. So, for example, if I have this container right here, we got some CO2, we got O2, and we got argon inside of it, right? And the total pressure, the P tot, is equal to 1,000 torr. Oh, Nick, the binder's right here. My fault. Okay. It's very simple to find the partial pressure if we know the composition, because all of these guys, they're ideal gases, so they have the same properties, same characteristics. And so all we need to do is take the total pressure, 1,000 torr, and then we can just multiply it by the percentage of the gas we're looking for. So since we're looking for oxygen, we can multiply it by 0.18, and that will give us the partial pressure of oxygen. That's basically what this law is saying. Okay. So oxygen's partial pressure will be 180 torr. Okay. So using the, I guess, very simple concepts about gases, we can derive a lot of different calculations from it. And this is another thing. We could find the mole fraction using the pressure, the partial pressure. Okay. Any questions on this one? Okie dokes. Okay, so let's move on to the next part. The next part, part 5, is about something called the kinetic molecular theory. Now, it's a very fancy term. But basically, this is just some information about gases that we use to kind of model their behavior and their characteristics and things like that. Okay, so you guys don't need to like memorize these like step by step. The AP test isn't going to ask you like, hey, what's the first point of KMT? But it's a good way of thinking about how these gas molecules move. And some of you guys might already think about these things just kind of unconsciously. And this is just to put it into words. So first, gases are made out of a lot of different particles. So if you have a sample of gas, again, it's made out of gas molecules. There's a lot of them. And the gas molecules are constantly moving, and they're flying around in basically random motion. Okay, they're just flying around all over the place. Okay, we talked about ideal gases, how the volume of the gas molecules themselves, they're pretty negligible. The gas molecules are very small compared to the volume that they take up. They don't really interact with each other. Okay, and energy can be transferred through the collisions, but the average kinetic temperature or kinetic energy is dependent on the temperature. Sorry, guys, I had a lot of MSG in my lunch. I'm like falling asleep right now. I can't talk. Okay, and then we use Kelvin temperature is proportion to the kinetic energy. Now, if you've taken physics, basically kinetic energy is just the energy that comes from something moving. So the gas molecules are flying around, right? So they have a certain amount of kinetic energy, and that's what determines the temperature. That's basically what kinetic molecular theory is. Okay, so if we could summarize it kind of very simply and concisely, it's gases are made out of molecules that fly around, and then the energy they have from flying around, that's the temperature. That's what the KMT is. Okay. All right, any questions about that? Okay, so before we move on, let's kind of look at it from a macroscopic point of view, so it's easier to think of. Okay, let's pretend these gas molecules are cars. Okay, so I drive a truck, right, and a motorcycle. So if I hit you with my motorcycle, or I hit you with my truck, which one would have more kinetic energy? The truck. Why would the truck have more energy? Yeah, because it's bigger, it weighs more, it has more mass. Same thing with the gases. We know that gas molecules are different sizes, different masses, right? For example, H2. H2 just has 2 AMU, right? So H2 is a lot smaller than, let's say, something like xenon, which is 131 AMU, right? And so the bigger the gas molecule, the more energy it will have if it's flying at the same amount of speed, right? So let's think of it this way. So we got H2 and we have xenon, okay? Let's say it is 100 Kelvin. It's the same temperature. Now, we said the temperature has to do with the kinetic energy, right? Okay. And so if they are flying with the same kinetic energy, I don't know if you guys took physics, but the energy is determined by the mass and the speed or the velocity that the gas is moving at, right? Okay, we said that H2 has a smaller mass, right? So if they have the same kinetic energy at 100 Kelvin, which one is flying faster? Yeah, H2 is flying faster. Okay, and that's the relationship that I want you guys to recognize. Okay, if two gases are flying at the same, or they're at the same temperature, the smaller gas has to fly faster in order to produce the same amount of energy, right? If I wanted to produce the same amount of force as my truck with my motorcycle, when I hit you, I'm going to have to drive that motorcycle a lot faster, right? In order to produce the same amount of force. Same thing with gases. Okay. And that's what this, what is it? This graph is kind of telling us. It's telling us that the speed, the smaller the gas, the faster it needs to go to get the same amount of kinetic energy. Okay. Yes. Yeah, smaller gas have to fly faster. So if we could summarize that in one sentence, it would be smaller gases, I guess fly is the wrong term, but they move faster than larger gases at the same temperature. Hopefully my hitting you with my car example helps you understand that, okay? No, I have not. Fortunately, I have not. Why did you ask me that? Is it because of a stereotype about certain ethnic groups not being very good drivers? Hey, you know what, guys? I'll be honest, I'm not that great of a driver. And I think Asians get a bad rap because there's no middle ground. Like, it's like Asian ladies driving like 20 miles an hour on the freeway, or like, yeah, or like Tokyo Drift. There's no middle, like, ground for there to be like a good driving stereotype. Yeah, I'm also actually, I'm not gonna say that. I don't want to incriminate myself on video. All right, let's move on to 5.18. So, on the AP test, you got to get good at reading graphs and charts. And so I'm going to give you guys about 2 minutes to kind of analyze this graph right here. And I want you guys to answer this question. You can talk with the person next to you, try to interpret it, but I want you guys to find out the fraction of molecules. So you can give it to me either in decimals or a percentage or a fraction of the molecules at 0 degrees Celsius with speeds less than 400 meters per second. Just analyze this graph, and I want you guys to see what fraction of molecules at 0 degrees Celsius has a speed less than 400 meters per second, okay? So take about 2 minutes to do that, see if you can figure that out.
0 degrees Celsius.
Mm-hmm.
And I don't know. Let's not.
Yeah, no, that's perfect. Good job. That was a great explanation. So yeah, it's going to be about 50%. You could say 1/2, 0.5, doesn't matter. And it is half, and that explanation is perfect. If you look at the blue line, which is 0 degrees Celsius, and we look at the chart, we count in increments. This is the peak right there, so about half of it is under the blue line. Okay, so that's pretty much how you would explain it. Great explanation, Robbie. Any questions? Yes. Huh? Because if you look at the slope of these lines, so it looks like this one might be a little bit more, but this slope is a little bit sharper, so you'll have more area underneath this part than you would on this part, because you see how it tapers out, so you'll have a little less area, or less sharp. This part's more sharp right there. Alrighty, let's move on to the next one. Okay, so kinetic energy, we just talked about this. It's the energy that's involved with movement, and it depends on two factors, mass and velocity. And the formula for that is 1/2 mv squared. And so this is how you would calculate the kinetic energy that something has. And we already talked about this. The smaller the mass, the faster something needs to go to generate the same amount of energy. Okay. Again, if you guys didn't get the example, if I want to hit you with the same force with my motorcycle as my truck, gotta rev that thing up. I have a BMW R1200. It's the one that cops drive. So everyone thinks I'm a cop.
What measurement do we use to measure?
It depends on your units of measurement. If we use grams for mass and meters per second, it'll be grams per meters per second. And that's going to be newtons. And so if you guys take a look at this, it kind of tells you the relationship between these molecules and the speed at which they need to fly at. So if you take a look at hydrogen, which is the smallest one, you see how it needs to go extremely fast in order, or the average speed needs to be much higher than something bigger like oxygen. Oxygen can move at a much slower speed and get the same kinetic energy, the same temperature as hydrogen. Okay, and then everything in the middle as well. Okay. All righty, let's move on. So a couple more terms you guys got to know. So one other characteristic of gases is diffusion and effusion. You guys probably have heard, actually, sorry, lost my train of thought. Anyway, diffusion and effusion, honestly, I think the easiest way to think about this is think about farts, okay? And I know I probably sound 7 years old talking about this, but let me explain diffusion. Okay, diffusion is when you mix one substance with another. So if you guys take a look at this part right here, it's just saying that when you get rid of a wall or a partition or open a door, the gas can move from one part of the container and spreads out to the other side. That's what diffusion is, okay? So let's just pretend there's a wall between you and me, and I rip a really nasty fart, right? While the wall is up, would you smell my fart? No, because the gas molecules are stopped by that wall. But if we get rid of that wall, my fart will push and diffuse to the other side of the classroom, and you guys will smell it eventually, right? That's diffusion. Okay, gases will spread out when you move the wall. Effusion is when a gas escapes from a container through a small opening. And so you guys can kind of see where I'm going with this, right? Your fart is in your body. A small opening opens up, and then the gas is able to go to the other side through that small opening. That's effusion. Yes, sure. You can write, for example, when I fart, I'm sure the AP grader will have a great time. Oh, dude, I'll give you a 5 just for that answer. No. But now you guys will never forget what effusion is. Just think about the 8th planet. Or 7th planet. 7th, my bad. 7th. Uranus. The planet, guys. Isn't it Uranus? I've heard Uranus, Uranus.
It's
Yeah.
technically pronounced Uranus. That's what the scientific community calls
Dude,
it.
whatever. They're just scared.
What you learn.
They're just scared to say anus. It's a medical term. All right. So now we got to talk about how these the speed or the rate at which these gases effuse and diffuse. Hey Nick, can you close that door for me?
No.
I don't need background music. My voice is perfect the way it is. Okay, so we're gonna talk about the rate or the speed at which these gases diffuse and effuse. Okay, so let's just say, for example, we're talking about H2. Okay, so if we have H2 and we have, again, let's look at our example with xenon. Okay, let's say that it's 100 Kelvin for both of them. They're both at the same temperature. Which one of these is moving faster? H2, right? This one's moving faster because it has a smaller mass. And so we can figure out and predict the rate at which a gas diffuses or effuses based on which gas it is. H2 moves faster, so do you think that it would move to the other side of the container more quickly or slowly than xenon? More quickly, yeah. So smaller gases will diffuse and effuse more quickly just because they are moving faster. I know that sounds really obvious, but yeah. So what I figured out, or what I thought about after I learned this, is that depending on the chemical composition of your fart, you can get it to spread faster in a room. What you eat, it depends on what you eat. So for example, I'll answer your question in just a second because I'm trying to make a very important point. The gas in your fart that makes it smell bad is sulfur, okay? S2 gas has a molar mass of 64, okay? And I calculated all this, okay? The other gas that makes a big part of your fart is nitrogen, 28 AMU, and also methane, 16 AMU. Methane is what makes it flammable, okay? And obviously water, so 18, right? So if you want to make your fart smell worse, you need more sulfur. So you can eat things like egg yolks. I don't know if you guys ever eaten a bunch of eggs and taken a fart, but it smells really bad. But that gas is going to be heavier because 64 AMU. So it'll take a lot longer for it to effuse across, or diffuse across the room. And so if you want your fart to go further, you gotta make it smell less, basically. That's the conclusion I came to.
So the stronger it smells.
Yes, exactly. And that's why I think it creeps up on you. You know, the really nasty smelling ones, it takes a while. But anyway.
Is this like a very quick reaction usually? Like it doesn't diffuse like pretty quickly?
It depends on the temperature and the size of the gas again. Yeah. So the hotter it is, the hotter it is, the faster it will diffuse as well. No, but yeah. Anyway. So if you want to work out before, you can increase the temperature of the gases in your body, and that way they'll move faster. So practical tip for you. Okay, so the rate of diffusion and effusion, it's summarized by Graham's law. It's right here. R has to do with the rates of effusion of two gases, and this assumes that you're at the same temperature. Okay, so you can only use this when it's at the same temperature. And U, or mu right here, is going to be the molar masses. Okay. Okay, but this is basically telling you the bigger the gas, the bigger the molar mass, the more slowly it will diffuse or effuse. And this is how you can calculate quantitatively the rates. Okay. I'll be honest with you, you don't use this formula very much. Maybe. Who knows? Who knows what will be on the test? Yeah, mu is a molar mass. Alrighty, guys. So we are actually almost done with the unit. We just have one more type of problem to do. Yeah. That was quick, right? It's because I'm making fart jokes. Everything goes faster when you talk about fart and food. I really like thermo. I think thermo is a lot of fun. think thermal might be next or next. All right. Let's go to the last section. So the last section is a type of problem, and it's going to be gas stoichiometry. I know. You will never escape Stoich in Chem. Okay, I still do Stoich when I prepare stuff for my experiments at home. Okay. Yeah, of course. I got this degree. I'm not just gonna sit on it.
Since you have like, do you get like any special privileges like purchasing like chemicals?
No.
You're only
I think I might be actually. I'm Korean. I've looked up how to make a bomb without a VPN. That was, I mean, this was when I was in high school too, but you never know. I am Korean. I am. I can be both at the same time. Did you know that? All right, anyway. So I am going to give you guys 3 minutes to try out this gas stoichiometry problem, okay? It's still regular stoich, but you got to incorporate the stuff we learned about gases. So ideal gas law, converting temperature from Celsius to Kelvin. Yeah, I know. It's synthesizing all this material. Avogadro's law, molar mass or the volume, the molar volume of gases. Okay, you got to combine all of that together. So it's a lot of fun, but you also need to remember limiting reagents and things like that. So I'm gonna give you guys 3 minutes, just try it out. I'll give 4 minutes, try it out, work it out with the person next to you, see if you can figure out. And then after that, I'll start going over the problem just so that we're on the right track. Okay, and then we got one more problem. And then I do have some more practice problems for gas stoichiometry, so we'll work on that till the end of the period, okay? Take about 4 minutes to try out this problem. So we have some information about our gases. So we have our reaction right here, already balanced, so we don't need to do that. It says that if you have 15 grams of sodium chlorate, I think, okay, 15 grams of this, and it reacts with 2 liters of chlorine gas, the pressure is 1.5 atm, and the temperature is 21 degrees Celsius. How many grams of ClO2 will be produced? So this is what we are looking for. Now, usually when we do stoichiometry, we start with grams and grams, right? The problem here, though, is that we start with grams and liters. And so in order to do stoich a little bit more easily, we're probably going to have to convert our quantity of chlorine gas into grams, okay? And then we got to do some limiting reagent calculations. All right, so let's start with chlorine gas. So it tells us that we have 2 liters of chlorine gas, okay? This is obviously going to be the volume. So the volume of chlorine gas is 2 liters. Now we have the pressure, the temperature, and the volume. And so what we can do is we can use the ideal gas law, PV equals nRT, because that'll allow us to find the moles of chlorine gas. So far, so good? Okay, so we're going to rearrange our equation. So the moles is going to equal PV divided by RT. Okay, let's plug in our values. The pressure is 1.5 atm. The volume is 2 liters. The R value that we're going to use is 0.0821. And then the temperature, if we convert to Kelvin, will be 294. Okay. Plug and chug that into the calculator and get 0.124 moles of chlorine. Something around that. If you got 0.12, 0.13, 0.11, that's fine. Any questions on that part? All right, let's do our stoich. So let's see how much of this our chlorine gas can make. So from here, it's just regular stoichiometry. We got moles of chlorine gas, so we got to cancel that out on the bottom of this fraction. We're looking for this guy right here, so moles of ClO2. The mole ratio is 1 to 2, so we can plug it in that way. And then we just use the molar mass of ClO2, and the molar mass is 67.45. And so chlorine gas has the potential to make 16.73 grams of ClO2. Okay. So that's this part right here. Okay. Now we have to do one more calculation because we have a different starting value. That way we need to find the limiting reagent. But from here, it's just regular Stoich. We got 50 grams of NaClO2. And then from there, we just do regular stoichiometry. Okay, so we got to convert this into moles. 1 mole of NaClO2. I didn't write down the molar mass. What's the molar mass? Thank you. Okay. And then we're going to, again, use the same mole ratio. This time it's 2 to 2, so 1 to 1. Okay, and then the last fraction will be exactly the same. I'm running out of space. Okay, and so your final answer, you should get 11.2 grams of ClO2. Okay. And so from here, we can find out exactly how much ClO2 can be produced, and it's going to be right there. All right, so that's gas stoichiometry. It's just regular Stoich. We just added the ideal gas law into it. Okay.
You sort of made me think that we had to add.
Yeah, I did. Temperature conversion, ideal gas law. Did I see something else? Well, you could use Avogadro's law. Yeah, so 1 mole is 22.4 liters at STP, things like that. Yeah. Guys, you guys know I just say things. Words just come out of my mouth. I'm not liable or responsible for these things. Oh, sorry. I am supposed to teach you guys the truth. Well, the truth is, I say a lot of things that I don't mean. Jesus said that. Brendan, we established this last time. I need Jesus more than anybody in this room. It's a reminder that Jesus is the truth, and I need him. Hey, the whole message of Christianity is that we need Jesus because we're not good enough, and I need him more than anybody else. Very obviously. I never said I wanted to. I just said I just use that as an example so you would understand rates better. Hey, but answer me this. You understand rates better, rates of effusion and diffusion better, right? You do, exactly. Because you thought about Mr. O hitting you with his car or motorcycle. All right, let's move on to 5.20. Okay, so this is another example of a gas Stoich problem. This one's a little bit different because you're not going to be doing full Stoich. Instead, you're going to be doing some conversions. I'm not going to spoil it for you guys how to do it, but I'm going to give you guys about 4 minutes to try this one out as well. See if you guys can interpret the problem and get the answer. After that, we'll go over it in just a few minutes, okay? Take about 4 minutes to do this one. Okay, guys, so this one might have seemed confusing because of HCl, but it doesn't seem like it talks about HCl. But let's go over this problem. So let's draw this out because I want you guys to appreciate my amazing art. But here we have a little, let's say we have a beaker, and we have a mixture of lithium carbonate, Li2CO3, and we have magnesium carbonate, MgCO3. Okay, so we have a container. We have, let's say we have a solution, and inside the solution we have Li2CO3, and inside of it we also have MgCO3. Okay, now because you guys are experts in ionic equations now, you should know these two are not going to react together, right? Because they both have the same anion, right? I mean, like, imagine not knowing that. Imagine not knowing that they're not going to react, right? I'm sorry I even brought up the possibility that you guys might not know that, okay? That was insensitive of me, I apologize. Okay, so you have these two compounds, ionic compounds inside the mixture, right? And then it says that they're treated with excess HCl, okay? So inside of this mixture, hey, I'll see you, kissing you. We're gonna add some hydrochloric acid, okay? Now, the $1 million question, is hydrochloric acid going to react with these guys? Yes, it's gonna react. So there's gonna be two reactions that take place. The first reaction is gonna be between lithium carbonate and hydrochloric acid. And then the second reaction is going to be between magnesium carbonate and hydrochloric acid. So that's going to be the setup for our two balanced equations. that make sense? So yeah, so if you have a mixture of ionic compounds where you have the same anion or the same cation, obviously they're not going to react because if you swap them, you get the same compound, right? So that's how that works. Obvious. I'm sorry. I even insinuated that.
You must not respect this.
I'm sorry. I forgot for a second how much I respect you guys. Again, this is another reason I need Jesus because I forgot to respect you guys. All right, so let's do the ionic equation. So this is a double replacement reaction. So the lithium is going to break off from the carbonate and react with the chlorine. So potentially we get lithium chloride. And then the other reaction or the other compound that we're going to get is H2CO3. Okay, and that's why the hint was there, H2CO3. This H2CO3 is going to decompose. It's going to decompose into liquid water, so H2O and CO2. And then from there, you guys just would have to balance that. Yes.
Would that require like the equation? Or...
No, you can just substitute it out, yeah. So this is actually something that I recommend knowing because it's weird, but this compound shows up a lot, and I would recommend knowing that H2CO3 decomposes into liquid water and carbon dioxide. Yes. You would lose some points, yeah. Especially, or if they told you that, you would be marked off more. But let's say on the AP test, you have something like this, you're probably marked off a little bit for not having liquid water and CO2. Alrighty, let's go to the next one. Next one, I didn't balance it yet. I didn't forget. You're gonna get MgCl2, and then again, same thing. You can get H2CO3, but that's gonna be H2O and CO2. All right, and then for the balancing, I think it's just that, and then just that. Yep. So there you go. That's part A. Doesn't my amazing picture help so much?
It was better.
I'm saying it's
The disrespect on my art. It is
I
art.
mean, art is subjective.
Beauty is in the eye of the beholder.
exactly.
And I think you guys might not be very beautiful then.
No, it's beautiful. What are you talking about?
Whatever. Okay, from there, it's very simple to calculate the total number of CO2, right? This is just going to be, so there's actually multiple ways that you can do this. You can do stoichiometry if you'd like, but easier way of thinking, actually you don't need to do stoichiometry at all because you have 6 liters of carbon dioxide gas. It tells you the product. So the amount of CO2 that you make is going to be 6 liters. From there, it's a very simple calculation with the ideal gas law, PV equals nRT. You can rearrange this for volume. And RT divided by pressure. It tells you that it's at STP, so you have most of the info that you already need. Oh wait, I'm dumb. Why did I rearrange for volume? I'm so sorry, guys. It's moles, yeah, exactly. I apologize. Like I said, I had a lot of MSG for lunch. Honestly. Yes. Salt. Yeah, salt on crack. So for your final answer, you should get 0.0893 moles of CO2.
Like, how would we, if we had to use like stoichiometry to do that, how would we do that? Because it said like the mixture is 10 grams.
Yeah, so the 10 grams of red herring, you don't need that information. It's not 10 grams of this, 10 grams of that. So you interpret it correctly. You don't know the percentage of both. Yeah, it's just there to mess with you. Alrighty, any questions? Okie dokes. So I am going to pause right there. Let's take a quick break. And after that, when we come back, we can go over some more gas stoichiometry problems because hint, hint, that will be on exam. Hey guys, quick redaction. I'm sorry, I made a mistake. Hey guys, I made a mistake for part B. It shouldn't be this answer. It should be 0.268. My fault. I plugged in the numbers incorrectly. Dude, I'm always wrong. Like I told you, I'm making this up as I go. Okay. Okay, so if you take a look at number 1, it says that we got 2 containers of gases. Now, the key thing that you guys want to know is that it is at the same temperature and the same pressure, okay? Same T and P. Okay, one of the containers has 14 grams of nitrogen. The other one has 22 grams of carbon dioxide. You want to look for which of the following statements below are true, okay? So let's look at A. Okay, the volume of the carbon dioxide container is the same as the volume of the nitrogen container, okay? So let's think about this a little bit. So it says the temperature and the pressure are the same, okay? Now, if you guys remember temperature and pressure, do you guys remember the law that it refers to? It was the Gay-Lussac law, yeah. Yeah, Charles is volume and temperature, but that's the one that's very close. So it's going to be P1 over T1 equals P2 over T2. Okay. Now, if you guys remember, gases expand to fill their container, right? So if you have the same pressure and the same temperature, right? And if we go to, we can also use the combined gas law for this. Okay, you can see that we can figure out what the volume is. So let's convert this into moles because moles will allow us to have a better way of quantifying and comparing them, right? Because if you have grams of one, grams of the other, then it's kind of hard to compare them, right? Because they have different molar masses. So nitrogen is, N2 gas is 28 grams per mole. So that's going to be 0.5 moles. Carbon dioxide is 44 grams per mole. So this is also 0.5 moles. Okay, so if you have the same moles of different gases, remember we're talking about ideal gases, you should be able to identify that same moles is going to equal the same volume. Sorry, it wasn't this law. I was thinking about a different law. It was Avogadro's law. N1 V1 equals N2 V2. And so by that account, we're going to have the same volume. So the answer is A. I know, it's right at the beginning, right? Sorry, I was talking about the wrong law in the beginning. My fault. Okay, but we can also go through the other examples to disprove all of them, okay? So let's look at part B. Number of molecules in the carbon dioxide container is greater than the number of molecules in the nitrogen container. Now, we know that 1 mole is equal to 6.02 times 10 to the 23rd molecules, right? So if you have 0.5 moles, that means you'll have the same number of molecules, right? But here it's saying carbon dioxide is greater, so B is incorrect. Okay, C, density of the carbon dioxide sample is the same as that of the nitrogen sample. Now that's not going to work because we're looking, if density is mass over volume, the masses are going to be different. And we just figured out the volumes are going to be the same, so that one is also not going to work. Okay. Average kinetic energy of carbon dioxide is greater than the average kinetic energy of nitrogen. Now, we said that nitrogen is 28 grams per mole. We said that carbon dioxide is 44 grams per mole. Okay, but we know that when it comes to kinetic energy is a measure of temperature, right? If they are at the same temperature, then obviously that they're going to be moving with the same kinetic energy. Thank you. And then speed, because nitrogen is smaller, it has to be moving faster because of the AMU. So this is also incorrect. So the answer is going to be A. Yeah. This situation, this works because they're the same amount of moles. So if they still equal to the same moles of each gas, then it would be A still. Then you wouldn't be able to solve this problem. with the information that you're given. Because if they're different moles, then the volume is going to be different from one another. You wouldn't have the same volume. Yeah, they're flexible containers. So the volume, yeah, the containers can change shape and volume. Yeah, if it was fixed volume, then yeah, volume would be constant. Yeah. Great question. Yeah, so that's why this test is annoying. There's so many like little words in there that you need, and you need to catch every single one of them, that it gets kind of difficult. But does that make sense, guys? Why it's A? Yeah. All right, isn't this fun? AP test questions. All right, let's go to number 2 then. Very similar. I don't know if these came from the actual AP test, but when you look at the AP test with gas law questions, it's very similar. Okay, so this one is a calculation one. Shouldn't be too long, so I'll give you guys maybe about 2 minutes to try this out. See if you can figure out what values to use, and then you can solve it. Okay, so I wrote down the variables that we have. So we have 0.01 moles, 127 degrees Celsius, 2.5 ATM, and the question is asking the pressure at 27 degrees Celsius at the same volume, okay? And so here, since volume is constant, we don't need to worry about that. It doesn't say if we added or got rid of any gas, so the moles also stay constant. So the only values that are changing are pressure and temperature. So this one is Gay-Lussac's law. So P1 is over T1 is equal to P2 over T2. So we're looking for the pressure, the new pressure. So we're looking for P2. And so if we rearrange the equation to P2, you'll have P1 times T2 divided by T1. Okay. Now from here, it's just plug and chug. Our original pressure is 2.5 ATM. We have to convert the temperatures though. So if we add 273, we'll get 300 Kelvin for T2, and then we'll get 400 Kelvin for T1, and then you should get a final answer about 1.88. That's the new pressure. So your answer is going to be E. You guys are getting less energetic and more depressed as we end class. This is great. This is great. Now the goal is, how can I get you guys sat in the middle of class too? Find a way. Huh? No, I'll find a way. Where there's a will, there's a way. Okay, we'll do one last one, guys, and then I'll have you guys go. Did you guys find any specific questions you guys wanted to go over? No? You guys good? Okay. I won't respond over the weekend, but you can. I'll get back to you on Monday morning though. Okay, we'll do one last one and we'll do the last problem on this problem set. So if you guys want to go down to 43. Okay, now the reason I wanted to do this one is because you're going to have to write an equation on your own. And I don't think we went over types of reactions very specifically in class. But if we take a look at this problem, it's asking what is the total volume of products formed at STP when 1.2 grams of carbon is burned. So let's start with the equation. Now we need to write the chemical equation. So obviously we're going to start with carbon because we're burning carbon. Anyone remember from their reading, which I'm sure everybody does, in its entirety by the day that it is due, what happens in terms of reactants when something's burned? Yes, O2, you combine it with O2. Okay. Anyone know the products of a reaction when something is burned? CO2, yeah, wow. Yeah, CO2 is always formed when something is burned. So if you guys ever see the word burn or combust, just remember one of the reactants is going to be O2. One of the products is going to be CO2. Usually there's also H2O. Okay, but here we don't have any hydrogen, so it's just going to be CO2. Alrighty, so from here, we don't need to balance because it's already balanced out. We're gonna just do some regular stoichiometry. We have 1.2 grams of carbon, and we want to find the total volume of products. Obviously, our only product is this. So we want to find the volumes of CO2 at STP. Okay. So I will give you guys about 3 minutes to try this out. We'll go over the answer, and then we'll be done for the day. We'll be done. Okay, so super simple. We need to convert from this guy to this guy. So got to convert it to moles, right? 12 grams of carbon per 1 mole of carbon. We have a 1-to-1 mole ratio. Now, this last conversion, it's very simple because all we got to do is see that, hey, it's at STP. And we know that at STP, the molar volume of a gas is 22.4 liters. So it's just one conversion, 1 mole is 22.4 liters. So we'll get a final answer of about 2 liters. The answer is B. And you got 2? Yeah. Yeah, the closest one. Yeah, so if you wanted to use the ideal gas law, that's perfectly fine. But this is just easier. So use the ideal gas law when it's not at STP. But at STP, you have a quick little conversion from 1 mole to 22.4 liters. So either will work. Yeah. Yeah, that's perfectly fine. Yeah. So this is the little shortcut you can use. But if you use PV equals nRT ideal gas law, you're totally good.